I can't see you, but I don't suppose I ever will.
Yeah, okay, sweet. Alright, so you can go ahead and start whenever you're ready.
So, yeah, you can see me, right?
Correct. Everything's set up perfectly.
Can you put the computer
Yeah, we
facing
can see
us?
your
Everything's set up, that's great.
Okay.
Jessica, sorry.
Okay, well,
Can you put the computer
that's
facing
great.
us? Should I? No, that's fine.
You've got quite an impressive program there, and I'm looking forward to seeing. I haven't managed to see the live stream yet, but I'm looking forward to seeing some recordings of the event, and other good friends there. Hi to everybody. Hope you're getting to know some of each other, and the best way to, I'm not very good at making speeches, so I thought probably the best thing to do would be to just talk a bit about my experiences on Scoraig over the last 35 years, because actually the stuff that you're probably most familiar with, like the most recent stuff, the rest of the book is only part of my experiences with wind energy. And I thought it might entertain you to see some history, so let's see if we can move on. This is a map of Scoraig, where I live. For those of you who don't know, it's up in the northwest of Scotland. I suppose the reason I live here is because as a child I spent a lot of time off-grid on the west coast, and it's a very magic sort of place to live. And so I moved here in, I suppose, 1974 or something, and without any particular intention to stay, and been here ever since. Here's a picture of the place where you take boats across the Scoraig. You can see the peninsula in the distance, and these are the sort of boats that we use to get across the water. And moving back in time to 1975, I think I have the ability to doodle on this now. This is my first window that I put on the roof of the house. I don't recommend putting windows on the roof of the house. At the time we didn't have any electricity apart from the 12-volt battery, and just to listen to music. And we used paraffin for lighting, and didn't really see much need for electricity, to be honest, but it was nice to have a means of charging a 12-volt battery. But putting the window on the roof was not a good idea. It was very noisy, but even just the very slight roughness in the bearings transmitted through the structure rumbled, and although it was wide open space, you still get quite a bit of turbulence on the rooftop. You're much better off putting it on top of the tower. Well, I was pretty happy with paraffin lighting for a while, but when I had small children around and began to get interested in possibly watching television or just having the convenience of electricity, even for a 12-volt washing machine, I started messing around with trying to build wind turbines, and it turned out to be a lot more difficult than I thought, because, well, they do seem to be quite a tricky technology, as you might have noticed, but I persevered with it, and I managed to get something working, and all my neighbours wanted one too, and so that's how I sort of went into it. If this had been a better place for hydropower, and I probably never got into it. I would probably got into microhydro, and to be honest, I would recommend to you guys, if you do find a site where there's potential for microhydro, you should always recommend that in preference to wind energy, because although wind power is it's sort of glamorous and it's fun and it's a challenge, it's not the easiest way to generate electricity. Here we've got a single-bladed turbine in Europe from the early years. I can't claim the ownership of this. I carved the blade for it, but it was my cousin who made it. He figured out that what we needed was the maximum possible speed. Well, I figured this out as well. To be able to generate electricity, we needed the maximum possible speed for the largest diameter rotor, and what that boils down to is a high tip speed ratio and being an engineer, he figured out that we needed a single blade to achieve that, to get the lowest possible solidity. So he did the teetering hinge and the counterbalance weight, and it worked pretty well until he got to the pitch control mechanism, but he could never really get that working right, so we had to abandon it in the end. This one on the right is from 1983. This was when I built quite a few machines at that time, and the furling tail is actually operated by a windscreen micromotor. So when the battery got up to a certain voltage, then it would actually furl the tail automatically using a windscreen micromotor to flip the top link of the tail hinge over to the other side of the central gravity, the other side of the bottom link. So these are some of my early experiments. Well, not experiments exactly, this is what I did in the early years. And I'm having a little bit of trouble moving forward. There we go to the next slide. The big challenge was to find a suitable generator that would work at low speed, and in the end the answer turned out to be a Jeep from a dynamo from an Austin Champ Jeep. Very high quality dynamos designed to work at 24 volts, and they have quite a low cut-in speed, around 1,000, just under 1,000 RPM. If you modify the field coils to work at 12 volts, you could get a cut-in at about 400, 450 RPM. Which was suitable for a two-bladed rotor about 1.5 to 2 meters in diameter. That could achieve that in about a 4 or 5 meter a second wind speed. Very different scenario from nowadays with permanent magnets, because we have to generate about 30-40 watts of energy just to energize the field coils. And so you could forget about charging in low wind speeds, 3-4 meters a second wasn't really on, because you didn't have enough energy then to even energize the field coils. So these were fairly high wind speed machines, but very efficient once the wind got up. We could generate 300 watts of 12 volt power, and we used them basically just for 12 volt lighting, using bulbs out of cars. Listening to the radio, watching 12 volt TV, and as I said earlier, we even modified washing machines to work at 12 volts. Just for the agitation and perhaps operating an electric wringer. The tail furling systems initially were operated by springs, but I found out after a year or two that the springs were generally the first things to fail. So I went to a gravity tail, and actually went to a pretty sophisticated design, much more sophisticated than what I would use now. The bottom link is a ball joint, simple ball joint. The top link of the tail suspension, you guys maybe at the end. It's probably not practical to take questions during the talk, although I would like to have done so. I'm just going to try and move this dialog box out of the way a bit so I can see my presentation. Okay, so I was talking about the tail hinge system, and in summary what I would say is that this was a more sophisticated but less reliable method of suspending the tail, which I would still use with a chain on a larger machine, but the simple pipe-on-pipe pivot works really well for just for its simplicity and reliability. It's good enough, although it doesn't give you the completely optimum shape of power curve that you can achieve by wrapping a seatbelt webbing around a can. So that's basically what I wanted to say there. I also wanted to point out that these dynamos weigh 25 kilos, so it was quite an effort to hoist them up on the end of a rope while standing on a little crossbar at the top of the tower, and then to assemble the blades onto that. But it was quite exhilarating. And yeah, here's this is probably beyond what you saw last time. It's a little bit repetitive for me, but I'm going to say it again. Back in those days, even then I was writing stuff, and this is probably my first book, if you like. It was a series of magazine articles that were published by the Centre for Alternative Technology under the name Scrapyard Wind Power Realities, and it explained how to build these sort of dynamo-based machines. You can see the blade carbon description is similar to what I offer now. It's been the same basic process of carbon blades that I've used since the beginning, although in the beginning I used 2 bladers so as to get a high tip speed ratio, whereas once I had control over the power speed characteristics of the generator, I went for 3 blades because they run much more smoothly and a bit quieter. Whereas the 2 bladers have an inherent vibration, especially in yaw, which makes them clatter a bit. And yeah, we had some quite nice cartoons in Scrapyard Wind Power Realities done by a neighbour, and some explanations, for example, of how to modify field coils in a wound field machine, where you have these 4 coils in series for a 24-volt machine. Each coil actually just needs 6 volts to energize its field. By cutting the sequence midway and connecting wires in, you can get 2 parallel pathways here, each at 12 volts, be able to energize the field coils quite satisfactorily at a much lower voltage, much lower RPM, and that made these machines feasible to use for wind energy, although it was still quite difficult to get any useful output below about 5 meters a second. So they were very much high wind speed machines. And actually we only got about 1 kilowatt hour a day out of them. But it's a funny thing that the value of electricity isn't really entirely proportional to its quantity. The first little bit of electricity is worth an awful lot more than what follows. And so 1 kilowatt hour a day was enough to revolutionize our lives much more than any subsequent 5 or 10 kilowatt hours that we may have got later from larger or more sophisticated machines. This is actually a contemporary photograph, but it shows the kind of batteries that we would have been using back in the 1980s. These are telephone exchange batteries, very, very high quality, durable 2-volt cells that we were lucky enough to get for scrap price. And it highlights the vulnerability of these systems to cost considerations for balance of system components such as batteries, inverters, and so on. In order to, it's all very well to be able to generate the wind energy, and you can produce a low-cost wind turbine that's reliable, efficient, etc. But you've still got to look at the economics of the storage of the electricity, and especially with these relatively high wind speed machines that we had back in those days, you were very vulnerable to calm periods of weather. And we were very lucky that we were able to get hold of these second-hand telephone exchange batteries. Actually, the picture gives itself away by the presence of a Morningstar charge controller on the wall. That's because these batteries are charging at about 60 amps. Back in those days, they would only charge at about 20 amps peak. And if you had about a ton of batteries charging at that rate, you didn't even need a voltmeter. You just see the lights get brighter in windy weather, and if it got really windy, then you might leave the lights on overnight to prevent the batteries overcharging. But there was no need for automatic charge control under those circumstances. And we didn't bother with an inverter. This is a modern inverter that you can get for, oh, I don't know, probably about $20, $30 or whatever. In those days, inverters were very expensive, unreliable, inefficient, whereas 12-volt lighting was actually more efficient than the incandescent mains voltage lighting of the day. So actually, it made more sense just to stay with the 12-volt system, and that's what we did. And they were largely made from recycled parts from the scrapyard, recycled cable, even recycled bulbs from scrap vehicles, etc. Can you hear me?
Yeah.
Yeah, you're still there? That's good. Okay, so I'm going to turn to the sort of guide towers that we made in those days. We used to basically just take a telegraph pole and support it with fence wires and then put a piece of water pipe on top of that and guy that with fence wires. My rule of thumb in those days was that the guy anchors should be roughly twice the tower height away from the tower, and that made a very low guy angle, so that the loads on the anchors were largely horizontal. You could pretty much just bang a fence post in behind a rock, and that made a perfectly good anchor. And you need to have plenty of guys, because although fence wire is durable and very strong, it has fatigue problems, and if livestock rub on it, it tends to snap. So it's a good idea to have multiple fence wires for redundancy purposes. But I'd still recommend fence wires as a good, effective, low-tech solution for guying wind turbine towers. This picture from 1980, it was before I learned to pass the wires down the middle of the tower. So one of the little jobs that you had to do every few days was to climb up and actually untwist the wires, because they just wrapped themselves around the tower as the wind direction changed. Climbing up and working at the top of the tower was very exhilarating and kind of simple, but at the same time it wasn't really the most efficient way to do it. And so at some point around about 1990 I learned how to do tilt-up towers, and I converted over to winching the machine up using a turfer winch, as in this right-hand diagram. And that's what I would recommend. Obviously, it's a much more satisfactory way to work. You can have all your tools around you on the ground and put the machine together very easily. But I do sometimes feel nostalgic for the days when I would climb up and enjoy the view from the top of the tower. It was great fun. Here's another picture of a machine from that era, with the ball joint at the bottom, bracket here, and a piece of seatbelt webbing wrapping around the cam there to get the correct tail furling system. In this case, I think the high-end stop is achieved by a piece of string, which is maybe a little bit optimistic, but it seemed to work okay. And the dynamo is covered with a piece of aluminium sheet to protect the junction box basically from corrosion. On the right you can see one of my earlier permanent magnet alternators, and right from early on I was aware that permanent magnets were the way to go. I even experimented with an axial flux machine. I haven't got any slides of that first axial flux machine that I built, but I was a bit unsatisfied with the results. Probably didn't put enough magnets into it, to be honest, with hindsight. But my first attempt at publishing plans for a permanent magnet alternator that actually worked well was my brake drum windmill plans in the 1990s. And the brake drum windmill was modelled on the style of permanent magnet alternator that I could see in North America, the Birdie and the Whisper, where you put ferrite magnets around the inside of a drum, basically. In this case, this one is from a larger machine where we used a 20-inch wheel rim from the truck and put magnets all around the inside of that. But the brake drum one was from a Ford Transit, or basically a Ford truck brake drum with magnets around the inside. I got stalled for quite a while trying to figure out how to do the stator, because stators would normally have external teeth on the laminate stack. Eventually I came up, well, I was encouraged by Gordon Proden to try just using laminates with a smooth outer surface and then gluing the coils onto the outside of that surface in an air gap that would be probably about 8 millimeters. And by gluing the coils onto the surface of the laminations in the air gap between the laminations and the magnets, you could achieve quite a nice permanent magnet alternator. It was very tricky to glue them on, and you didn't have the ability to adjust the air gap. So it was a lot more difficult than the axial flux design, but it worked pretty well. At that time on Scoraig, we started building much larger machines using hollow plywood blades. I haven't published the design for these Nirvana machines, because to be honest, I don't think that it's a particularly attractive option for somebody who just wants to build one or two. There's an awful lot of tooling involved, basically, in making these blades. We had to cut out molds from heavy plywood to shape them, and then form this jig with the lower surface supported here on the lower surface is supported on the bottom halves of the blade section shaper mold things, and then the top half we close down on top of this upper piece of plywood, and then it will be glued along the trailing edge with a spar in the middle. This shows the assembled blade, and then putting the hub together is quite a nightmare of complexity. But it was fun to design, and we've got a few of these machines running. They're about 5 inches in diameter. At that time, I got recruited for my first developing world project in Zimbabwe, and we actually used a brake drum style alternator for that. And the company that built the prototype, Paratronics in Harare, went ahead and commercialized the design as an African Wind Power AWP turbine. Initially, it was intended to be for rural electrification, and they did one rural electrification project for a village in the Eastern Highlands. But there's not a great deal of wind in Zimbabwe, and the big attraction there was to make something that they could get export dollars for, exporting into South Africa or even into the United States. So I imported quite a few into Scoraig, actually. We've still got about 10 of them running here. They're one of the main workhorses for wind power on Scoraig to this day, using this axial flux, this radial flux brake drum style alternator and furring tail. The design modifications did cause some headaches. The fiberglass blades initially had very poor quality, not nearly as strong as wooden blades. It took them a while to develop fiberglass blades that were reliable, and even now I would say that half the machines on Scoraig have wooden blades rather than fiberglass ones. But African Wind Power did finally produce reliable fiberglass blades. The other thing was that my design was very simple, with the wires simply hanging down the middle of the tower, and they would just dangle down here, and gradually over a period of years they get twisted up. On some sites they get twisted up more rapidly than others. But to get into the American market, they found that the Americans weren't really comfortable with this concept. They just couldn't sleep at night with the idea of these wires twisting up inside the tower. So they had to provide a machine with slip rings. And so they modified the design to incorporate slip rings like this. Unfortunately, as part of that design modification, the central part of the yaw, assembly was critically weakened, and there was a stress concentration at the bottom of that yaw shaft, which meant that a large number of these machines failed in the United States, and the warranty implications of that meant that they lost their US distributor, and that was kind of the end of African Wind Power as a company. The Zimbabwean economy was going down the tubes, and unfortunately that meant that they couldn't continue to export, and that was the end of that. But it was quite a nice process whereby a developing world country could be manufacturing something and exporting to the USA in a reversal of the normal economic trend, and getting US dollars into their economy that way. Here's a slightly more detailed shot of the alternator. Initially I thought it would be best if they used a brake drum for this, but it turns out that in Zimbabwe and a lot of countries, I believe, it's cheaper to actually get a guy in a foundry to cast a brake drum for you than to import one from Europe or from North America or Japan. So they cast the drum to whatever shape I wanted. So I just specified a size and shape for it. And then they made this laminated stator to go inside. Now, making the laminations for the stator was a really big challenge. And although this was a company in the capital city, Harare, who were quite conversant with making transformers, etc., they found it really quite a challenge to stamp these laminations, and it was only just possible during the project to achieve that. So that made it clear to me that the laminated stator wasn't such a great idea for local manufacture with minimum of tooling, etc. It was just a farce. They had to use a very, very high-tech stamping machine and a very expensive indexing gear, and it was very difficult to achieve that, to achieve the necessary precision in the manufacture of the stator laminations. I'd like to look therefore at a comparison between these two alternator configurations. You've got on the left here, you've got the radial flux design, where the field goes across a very small air gap into a laminated core. This would be the design of the African wind power, or also the Bergy and the Whisper, on which I suppose the design was loosely based. The advantage, I suppose, is that for relatively small investments in magnets, you get quite high field strength, you get good electrical output in relation to the cost of magnets. The disadvantages are that the laminations are really difficult to manufacture, and you've also got quite a few downsides with having a laminated core. One of them being the drag in low wind speeds, the parasitic losses, the hysteresis loss, and the eddy current losses in the laminations. Another drawback of using laminations is that they increase the self-inductance of the coils so that there's a limited amount of current you can actually get out of these windings, and they have a tendency to overspeed when they get up to a certain current output. So that means that you have a tendency for the machine to run away unless you limit it to a relatively low output. It's always going to have a bit of a tendency to overspeed. Whereas on the other hand, the axial flux machine is really easy, I think, by comparison to manufacture. You don't have any curved surfaces to deal with. You're working with flat stator, flat rotor. The main downside being that you do have to throw a lot of magnets at it to make it work, because you have this very large air gap between the two rotor discs. Since those days in the 90s, I haven't bothered with the radial flux machines anymore. I just do axial flux. On this question of radial and axial flux, you might be interested in looking at a slightly different topology, if you like. This is the Proven wind turbine. I worked with Gordon Proven a bit during the 90s, prototyping one of his machines and optimizing the performance. And this is me winding one of his stators. The machine is axial flux, and it has these two magnet motors that look very familiar. But the stator will look very unfamiliar because it's a toroidal core. It's basically a steel core wound from a strip of laminate material, and the coils are wound toroidally around that. So each coil is wound around the core like this. Here we go, right around the core, and you get a whole series of coils wound right around that core. And the magnetism, the two poles facing each other would both be north, and then you have two south poles. So the magnetism goes into the gap, into the core, along the core, through the coils, and comes out again as another pair of magnets. It's very efficient actually, because the core acts as a flux concentrator. So even with ferrite magnets with a relatively low flux density, you can get a very high flux density in that steel core. And although I've never actually built any myself, this is certainly a very viable option for building permanent magnet alternators. I don't see why it shouldn't be done in a relatively low-tech workshop. And yeah, that's something for you guys to think about if you get bored with the alternator designs that we've been using up to now. Around about 99 and 2000, I got another developing world job working with Intermediate Technology Development Group, ITTG, I called Practical Action, and that got me to travel quite a bit to Sri Lanka and Peru. I think Udaya Hetigoda might be with you today, which would be fantastic. Hi. He's the guy that I work with in Sri Lanka, and I also work with just a small group in Peru, and I believe that did lead to something, although I wasn't really a part of the ongoing evolution of the design in those two countries. But it was a privilege to participate in those programs and to get the opportunity to develop my alternator design as part of them. One spin-off from that was that I was able to produce a manual around about the year 2004 constructing permanent magnet alternator, and that actually went onto the internet as a free document. You'll find it for sale quite often on the internet too, but it's been quite a useful document, I think, for people who wanted to build their own permanent magnet alternators. I regret now that I used such a complicated stator design back in those days, because the stator is shaped sort of like a pudding bowl. It has these skirts, which was quite difficult to manufacture, and meant that you couldn't check the air gap at the back. And there's no real reason for this. I think I just thought it would make it stronger, or possibly look better, or possibly be better weatherproofing for the bearings or something. But anyway, that's one of the things that's fallen on the wayside with a simpler and more practical design as the designs evolved over the years. So between, say, around about year 2000 and last year, I've been travelling around teaching a lot of courses, and that's been in itself quite an education for me, working with people all around the world. They've brought a lot of new ideas to my design. They've helped me to focus on simplifying the design, making it more doable, more reliable, and more efficient and simpler in all ways. Culminating in the recipe book designs that you're probably most familiar with, where there's a whole range of different machines with wooden blades and axial flux alternators and furling tails. Looking back at that now, from experience of running those machines, my main criticism would be of the neodymium magnets, the corrosion problems you can see here in this picture have proved to be, certainly in a maritime climate, such as where I live, or in, for example, Caribbean, Nicaragua, you'll be hearing to corrosion. Ferrite magnets, on the other hand, I've been working with since the 90s. I've still got some of the old magnet rotors from those days. They still work, they're very rusty. The steel discs have rusted. But the magnets themselves, you could have fly off, land in a ditch, get chipped, lie there for years, fish them out again, put them back in the magnet rotor, and they would still work fine. So a much more reliable magnet technology, much cheaper. The only disadvantage being that they have lower magnetic flux. And so I decided recently to revisit the ferrite design. A couple of years ago, I redesigned the alternator using a much larger density of magnets. As you can see on the right, it's got 12 magnets rather than 8 for the 300 mm diameter rotor disc. And this is possible because the magnets are much cheaper now. It makes more sense with cheap magnets to cover the disc with magnets. When the magnets are expensive, you'll get the best bang for your buck by spreading them out. But if the magnets are cheap, cram them in there. And I also discovered that for magnets that are crammed onto the disc like that, you're better off with a different type of coil shape, a triangular coil shape, where the hole in the coil is no longer the same size as the magnet. That really doesn't work when the magnets are crammed together. To get the optimum output, you can actually get a much higher density of copper in the stator as well. You can see the static coil winder here. It's not that much different from the recipe book coil winders, but it's a triangular triangular former in the centre. And after a couple of years, I actually managed to get a manual, construction manual in print and also out as an ebook. I've called this the 2F design. I haven't attempted to produce a wide range of rotor diameters within the one document this time. It's just a 2-meter diameter ferrite machine. But as usual, the main focus is on simplifying the construction, making it as simple to build, as reliable and efficient as possible. We've got a few of these out. We've been able to do a power curve test on one. Together with John Deary, we've done a lot of power curve testing here on Scoraig. And one of the best performing machines was actually the 2F, the first prototype one from a couple of years ago. So I'm very pleased with the design. And it just shows that the design process the recipe book isn't the be-all and end-all of the design process. There's always further to go, more stuff to try. Another of the new features within that design manual is that I've simplified the blade carving process. I've been criticised in the past for making the blade too elaborate, having too many stations, too many stages, too many processes. For me, it's simple because I've done it so many times. I'm very quick, and so I don't get hung up on all these stages. I just do them and get on. But it can be quite daunting. I think the complexity of the blade design. So with the 2F design, I've gone for a simpler blade carving process where the drop and the thickness of the blade are both done in a single carving process. It's necessary to take measurements from the back of the piece of wood to do this. And I've also gone for a smaller number of stations. And that's actually proved to be quite successful. It's difficult to compare exactly because you can't teach the same person both blade carving techniques at once. It would just confuse them out of their wits. But the simpler blade carving process does produce very nice results. And it may be that in the past I've been too fussy about precision and having too many stations and too many stages, and maybe this is the way to go. I've also gone for I don't think it's as attractive looking, but I've gone for a quite practical solution of just using a piece of what you might call 4x2 timber, what we called it before. And it's actually 100 by 50 millimeter. And that's generally more easy to come by than the wider pieces of wood that are needed for the recipe book designs. So it's all about making the design more accessible and simpler. We did actually build a 3F machine in Denmark last year, a 3-meter diameter one. When you built a couple of these, and it works really well too. I haven't actually published the design for this, but it's simple enough. I do have a design if anyone's interested in building a 3F or even a 4F. I've got design documents for these, so just get in touch, and it'd be great to collaborate on some prototypes for these. Coming back to what I've been doing here on Scoraig, to finish up, I'd like to talk a little bit about my own big wind turbine, my big windmill that I've had in preparation for some years. It's got a 66 centimeter diameter magnet motor, and the blade diameter is 5.6 meters. I think I just got a bit scared by the size of the whole thing and put off finishing it. But eventually I realised I needed help, so I got a friend, Jonathan from Austria, to come over and help me a year ago, and we finally got it finished. Hi Jonathan, you'll see him, you'll be introduced to him during the conference, and it's great to see you guys all getting to know each other. This is the stator. And this is the machine assembled. The stator has 6 mounting points on 3 legs, each of which supports a pair of stator mounts on a piece of flat bar. So it's a sort of spider arrangement. The tail is an A-frame design. The bottom leg is on the ball joint, the upper one is on the chain that wraps around the cam here. So this is a return to the seatbelt webbing type of design that I used back in the 1980s. So here you can see the machine being erected for the first time. That's the ball joint there. It's actually a it's actually a trailer hitch ball joint, so that I could have something that was easy to replace. And the top end is supported by a chain. And there is the machine in front of my house. Here you can see a bit of detail of the chain wrapping around the cam on the top end of the A-frame. And here is the stop chain for when it swings out in low winds. That's to stop it at the bottom of its swing. Another interesting feature that I'd like to talk about with this machine is the simplicity of its maximum power point tracking design. This is basically a 48-volt battery charging machine, but simply connecting it to a 48-volt battery has a number of disadvantages that we've seen with all of the permanent magnet machines. As the efficiency increases, the problem that you have, the more efficient the alternator becomes, the less variation in speed there is, the less variation in voltage, and the less internal losses there are with the alternator. The more your alternator is just working at a fixed RPM, and that doesn't really suit the blades. What the blades want to do, 3 meters a second, they might want to run at about 60 RPM, whereas in 12 meters a second, they might want to run at 4 times that speed. 240 RPM, and obviously the alternator voltage is going to vary quite a bit. So the solution that I've come up with in the Nirvana design is to put heaters in series with the battery. So this is a schematic where you have the windmill here with the brake switch on the AC side of the rectifier. Going into the rectifier here, I hope you can see my arrow. No, you can't. Okay, here's my arrow. So the windmill's there, the brake's there. Here's the rectifier, and the output of the rectifier, the negative goes straight to the battery, but the positive, instead of going directly to the battery, positive passes through some heaters. And in this particular example, which is how I heat my house, it goes through a couple of heaters, one in the hallway and one in the bathroom, and at 35 amps charge into the battery, which I guess is around about 2 kilowatts into the battery. You're actually generating about 3.6 kilowatts because you've got about 1.5 kilowatts going into the heaters. The advantage of that is, well, you get more power out of the wind turbine for the same output current, and you get much higher operating voltage at high speeds, which allows the blade speed to vary. So you're basically achieving the sort of so-called table or power curve that you would get in a maximum power point tracking controller, but without the additional costs and complexity and vulnerability of that maximum power point tracking controller. So I think it's a great way of milking some more energy from the machine. In low wind speeds, you've got pretty good efficiency. Your losses into the heaters are relatively small. As the wind gets stronger, your batteries are charging quite hard, and you're generating quite a bit of heat. There isn't any way of manually adjusting those proportions. You're kind of locked in, and in the summertime it can be pretty annoying because you have to open all the windows. But through most of the year, it's quite handy to have some heating in the house, and that comes as a free bonus in addition to the battery charging, which is the main motivation for having the wind turbine in the first place. And so we've cut down considerably on the amount of fuel that we need to heat our, well, it is a very highly insulated building in the first place. But it's just another trick for making wind energy simpler and more efficient. This isn't particularly simple. This is my wiring in my boiler room where I keep all my inverters and charge controllers. I've had to buy a second inverter because of all the power that we're generating. We do need to run an awful lot of electric cooling devices and heaters and stuff, so I've got a second 3 kilowatt inverter and various charge controllers, including the Midnight Classic, which I'm testing out on the African wind power machine Iron House. It has increased the efficiency a little bit, and I have to say, yeah, you can get an enhanced efficiency from permanent magnet alternator wind turbines by using maximum power point tracking controllers. At the moment, I think they're still a little bit too expensive. They might be competitive if it weren't for the fact that you have to also include some kind of voltage clamp to protect them against overvoltage. And Midnight Solar have provided a voltage clamp, which you can see on the left here, which costs about twice as much as the controller itself. So really, I can't say that I would recommend purchasing these products at this point, because you could build a second wind turbine basically for the cost, and you would get twice as much power in low winds. Whereas these will only give you a certain amount of enhancement of power, most likely in high winds where you're less likely to need it. But it's an interesting technology to watch. I think as power electronics get cheaper and cheaper, we really need to consider using power conversion as well as just rectifiers and charge controllers. We really need to think about using a kind of electrical gearbox to optimize the output of the machine, and that would be in the form of a maximum power point tracking controller. So it's a project, maybe something that a student could work on for a low cost maximum power point tracking controller for developing world application. I don't know. So yeah, that's all that I've prepared for you this morning, and yeah, that's probably all we have time for given the technical glitches. We're probably running a bit behind anyway. I'd love to answer some questions if you have any. Otherwise, that's it for me. Thanks.
Does anybody have a question? I'm sure a lot of you guys have. Do we have time for
any questions?
Okay. Do you want to come up or speak loudly so he can hear you, and then you can go on and answer your question? Who'd like to go first?
I'm going to need that repeated, I'm afraid.
If anybody wants to ask a question, it's better to go on the microphone, I think, so that you can hear it.
Oh, yeah, I can't hear anything. No. I can only hear the murmur of voices.
Hi, Hugh, this is Esteban.
Hi there, Esteban.
Great to hear you. I heard you mentioned very quickly the wires that you use for the tower, like the fence wire. And
Fence wires, yeah.
I wanted to know, I mean, which disadvantages, or why would you not recommend it, or why would you recommend the other wires in the first place? You mentioned that they were good enough and that you do recommend them, but which are the advantages or disadvantages of using it?
Yeah. I would say the advantages are, low cost, very, very durable, very strong. And they're something that you can probably obtain quite easily in agricultural communities. I'm not sure, certainly in Scotland they're used a lot for fencing. We use the 3.2 metre diameter high tensile wire, and it comes in 400 metre reels, and it's very, very cost effective. These are the advantages. Disadvantages are that there's perhaps a little bit more skill with actually handling the stuff. It's a bit like a spring. It's very, very difficult to bend, and then if you bend it too much, it snaps. So tying knots in it is a little bit challenging. And then this question of it snapping is the main disadvantage. If you bend it repeatedly, it will snap, it will fatigue. So you have to use multiple wires for redundancy, so that if one of them snaps, you can hopefully notice that and replace it or repair it before the machine actually falls down. And we have had occasions where they have actually fallen down on Scoraig. It doesn't happen every year, that every 10 years or so you will actually get a machine pulled down because nobody noticed that the guy works with snapping. So yeah, it's mostly about the ease of the simplicity of handling the steel wire rope. I think once you've been shown how to do it, it's a pretty simple process. It's easy to handle, easy to adjust, it's flexible, and so that would be my main reason for recommending the steel wire rope. Steel wire rope does have pretty bad corrosion problems sometimes. I think we were talking about it a few years ago with Blue Energy, and the best solution that we came up with was to soak it in linseed oil. But that's the established best method of protecting steel wire rope from corrosion. But with fence wire, you don't have those corrosion problems. So yeah, that's basically the pros and cons. And with tilt-up towers, I have gone more towards using steel wire rope in recent years, especially since I can get it second-hand from anemometer towers at no cost or for free. But fence wire is still something that I would recommend, provided you are willing to get up the learning curve and provided you are aware of the risks inherent, because it can snap if livestock rub on it repeatedly.
Okay, thanks.
Anyone else? Yeah.
Hello, Hugh, this is Scoraig. Can you hear me?
Yeah, I can hear you.
Okay, great presentation, by the way. I was wondering about, you mentioned you built some two-bladed machines early on, and about the vibration issues. Did you try any teetering hubs for any of them?
Yes, yeah. Actually, as a matter of fact, it wasn't me, but my cousin who built the single-bladed machine. When the single blader didn't work, he went to a teetering hub. He had me make a large two-blader, and we built a teetering hub on that. Actually, it worked okay. Ultimately, what happened was I think the teetering stops broke, and the blades hit the tower, and we went to the three-bladed design. But yes, that is a valid method of reducing the stresses. Ultimately, if you get turbulent conditions, then you will see a lot of teetering action, and the blades will hammer on those teetering stops quite hard in turbulent conditions. So it's not a complete solution, but you can reduce the amount of vibration inherent in that two-bladed design by using a teetering hub. The way I got around it was basically just to build the machine pretty rugged and to put up with a fair bit of vibration. In the early years I used springs on the tails, and they used to generally fall off pretty quick because of all the vibration in turbulent conditions. But if you can get a reasonably laminar airflow and minimize the turbulence and build the machine robust, and I think the two-blader is still a valid way to go. It's going to be a bit more noisy, but it's going to be lighter or more electrically efficient, or it'll catch in basically on those higher RPM. And by all means you could try a teetering hub as well. I think it's worth the extra complexity.
No one else? That's all we have? Great. I think that's all we have for now. But would you like to thank him, for taking his time and being so patient, and even you guys. So I want to give him a round of applause. To the next thing. So we'll say bye to Hugh. Thank you so much.
Bye.
So you're gonna go first, right?
It works, but I can't find the
What happened to